Well, we're going to look at lesson 5.1 today. So here's your attendance link. If you want to scan that with a phone, if you want to go through, maybe you're on your phone and you need a different way of getting there, what you should do is go to your digital classroom, which I'll just show you from Google Classroom. Power School Learning will work as well. And we'll go to chapter 5, which I guess I can move my chapter 4 down. I don't need this up at the top anymore. We've completed chapter 4. So let me adjust this downward. Almost there. Moves as fast as I can. All right, there we go. So if you go up to chapter 5.1, chapter 5, lesson 5.1, and open that up, that's where we'll be today. The fact that you're listening to me means you've taken care of number 1. You're either here in person, which I have some in person. I have 31 on the Zoom. And later, if you need more help, you can always come through and do it YouTube as well. But you're taking care of number 1 out of the 4 things for each lesson. Number 2, just a reminder, we have to fill out the attendance. So there's another way of getting to this attendance. So even if you don't want to use this link, you can use that number 2 right there to take your attendance. And then after you do that, I would suggest you open up number 3. It'll take you to Power School Learning. If you slide down, you can hit that start exam. Mine says resume because I've already clicked it before. And you will have your problems that we're going to go over today listed here. So I would have that open if I were you. I'd also open up your pre-programmed calculators. That's list. We'll use 2 sets today. I'm going to be using basic right trigonometry quite a bit. So I'll open that one up. And I'll have one problem where I use another. So I'm not going to close this tab just yet, but I will momentarily. All right. Let's take a look at problem number 1. It says find the exact values of the 6 trigonometric functions of theta. So we had rules in chapter 4, specifically on lesson 4.1. I told you if you're solving a triangle, you want to make sure your 2 angles are located where?
On the x-axis.
X-axis, very good. So this is not in the right form. That's on the y-axis. So I rotate it around. And I could solve it like that. And so my 8 has become my y. My 10 has become the hypotenuse. There's my theta. There's my right angle. My x is unknown. So what we could already do, so the reason I wrote up this right triangle trigonometry, I'm not going to use any of this other stuff. I just open that up to have a calculator and also to have the ratios. So I could already find the first of the 6. I know that sine theta is going to be the 8 divided by 10, the y divided by h, 8 divided by 10. And we could simplify that fraction. What number goes both into 8 and 10? 2. So that could simplify to become 4/5. Now I'll let you solve the other 5, but before I do that, let's review how would I find what x is since we don't know what x is right now.
Pythagorean Theorem.
Very good. Very good, Jasmine. So if I use Pythagorean Theorem, whoops, forgot the T there. Pythagorean Theorem, which you learn in, like, I don't know, 7th grade, that it's a squared plus b squared equals c squared. Well, I use x, y's, and h's, so I'm going to say x squared plus y squared will equal our hypotenuse squared. So if I substitute in the values, we have x squared plus 8 squared will equal 10 squared. A little mental math here. Jasmine's spoken up a few times. Tonight I've heard. Let's get someone else. What is 8 squared? 8 times 8?
64.
Very good, Martin. All right, and someone else. What's 10 squared? 10 times 10.
100.
There we go. 100. All right. to solve. And right now I need to get x squared, or x rather, isolated. So the x squared is being added by 64. So the opposite of adding 64 would be to subtract 64. And so we have x squared equals 100 minus 64 is 36. And now what's the opposite of a square to get x isolated?
Square root.
There we go. Now normally in math, anytime you add a square root that's not originally there, you need a plus or minus with it. However, since this is given a real triangles always have positive links. We're only going to take the positive value of 6. And so from there, if you're listening later on and not live, you can just pause your video, but I'll give you a second for everybody else to go solve for your other 5 ratios. All right. Example 2. If sine is 5/13, find the exact values of the 5 remaining trig functions, values of theta. All right, so they've given us one, and we got to find the other 5 this time. I'm going to give us a little triangle to help us out, but before I do so, I'll recommend that we rewrite sine as being y over h. So y over h is 5. Y over h is 5 divided by 13. Now, for those of you who are spatially really good, you could just set up your Pythagorean theorem and go from there. But for others, it might be helpful to have a little diagram. What we know is that we have a positive y value and an h value that's always positive, a 13. We don't know our x, so x can move either way. This problem doesn't tell us anything, so I'm just going to assume it's positive for this visual diagram. So I have 5 units up there. Let's say 1, 2, 3, 4, and 5. So this is a y value of 5. We don't know x, but we do know our triangle has a hypotenuse length of 13. So it needs to be quite a bit longer than 5. So this is not really drawn to scale, but I'm just going to leave it like that. So here's my right angle. And so we'll say h is 13. Now, technically, do I know if it goes to the right or the left? No, I don't. But what we do know is that y is 5 and h is 13. So we go through and do the Pythagorean theorem again. So we have x squared, let me write it over here, x squared plus y squared equals our hypotenuse squared. And so this time the 2 numbers I'm working with is 5 squared. That's so ugly. Let me try it one more time. There we go. 5 squared and 13 squared. All right, mental math time. I've got a 5 squared and a 13 squared. What do we get for 5 squared?
25.
25.
Very good. I heard a lot of 25s there. And what about for 13 squared? A little bit harder. How about 169? And so to solve this, I need to isolate the x, which means I need to subtract 25 to get rid of that plus 25. And so x squared would equal, this is 144. And then again, we take the square root. And this time, since this is not a real diagram, we should have plus or minus. Because my diagram might not be accurate. Maybe this triangle should go left. We don't know that. So it should be plus or minus 12. Now, on the answer choices, I did not add in plus or minuses. So you're just going to use the value positive 12. You'll just assume it to be positive 12. And you can solve for your other 5. And if you're, again, not listening live, just pause the video. You now have the ratios listed here and your diagram there. Just pause the video and get your answer. Let's take a look at example 3. It says if triangle ABC solve triangle ABC if angle A is 33 degrees, B is 9, and C is 13. So let's take a look on this one. We don't know if it's a right triangle or not, but we do know angle A is about 33 degrees. So I'm just going to say somewhere in there roughly. I'm going to represent this as angle A and say this is 33 degrees. B is the short length of 9. Now notice it's not going to be directly across from the A. That would be lower A over here. So I'm going to put B equals 9 right there, which means this will be capital B. And little c, lowercase c, is 13. That's across from capital C there. I'm going to go ahead and connect this. And so now I try to solve this. We don't have a right triangle, so I would not be using right triangle trigonometry. So this is the problem I mentioned, that we're going to use a different calculator. So I'll ask the question, do I have a completed set or a pair? Do I have two A's, two B's, or two C's? No. So if you do not have a pair, what you use is the law of cosines. So law of sines is for it having a pair. Law of cosines, no pair. So here's my values. And so when I open this up, what I need to check out is, or I need to plug in my values here. Capital A is 33. Little b was 9. Little c was 13. A is unknown, so I'll put an X there. Take that off. So the answer should be the intersection, or you could just look right there. The answer should be 7.33, and it says 7.332. You can notice that's the same number right there. So we just solved for little a over here. That's approximately, if I round to the nearest tenth, 7.3. Now, once you know that, you could use law of sines and say, hey, I've got a completed set. And use law of sines to find your next side. Or the other thing you could do, since you're using the calculator, is probably the easiest. And by the way, the algebra, what just happened? Let me back up for a second. The law of cosines is this formula: a squared equals b squared plus c squared minus 2bc times the cosine of capital angle A. So basically what happens, if you need your a, you would take the square root of both sides. So a would be the square root of 9 squared plus 13 squared minus 2 times 9 times 13 times the cosine of 33 degrees. That right there is the math that the calculator did to get that number. Which is approximately 7.3. Now, what we could do is to find any other piece, I would just rearrange my formula. For example, if I wanted to find capital B, I would use the formula b squared equals a squared plus c squared minus 2ac times the cosine of capital B. So what I'm doing now, if you look up here, I'm exchanging any a and b that are written out. Any a became a b and any b became an a. Okay, caps for caps, lowercase for lowercase, all the way across. And so how would I do this on my calculator? Well, on my calculator, I'm just going to put the b value in as a. So this a becomes a 9. Instead of this b, I'm going to put in the answer is 7.3. Whoops, 7.3. And this angle A is now unknown. That's what we're looking for. And so the solution here would be, this ends round to the nearest degree, would be about 42 degrees. This right here is 42 degrees. So again, on this one, if you solve this, you would have 9 squared equals, A was 7.3, C is 13, minus 2 times 7.3 times 13 times the cosine of B. And you would go through your algebra to solve that. You'll subtract those two values over, and then you would divide by this front portion and then take the inverse cosine. And you'd come up with that capital B is approximately 42 degrees. Oops, it's just the calculator does it a lot faster than we do. Last part, in any triangle, how many degrees are there in the whole triangle?
180.
180. So a shortcut is to find angle C. C is going to equal 180 minus the 33 degrees of angle A and minus the 42 degrees of angle B. So 180 minus the 33 minus the 42 leaves us with 105 for angle C. And that should be a squiggly because we rounded the B. That's not an exact value. So this will be not an exact value either. So there you have it. That's how you do the bell ringer and review from from chapter 4. So here we go with chapter 5. Chapter 5. Well, in chapter 5, you have one job to do. And I need you to do it better than this guy. Okay, so chapter 5, a lot of students look at it and they're like, oh man, it's difficult, it's difficult, it's difficult. Well, I want you to really focus. You have one job to do. And I want you to just stick with me and try to follow what I'm doing. What you're gonna learn is chapter 5, we don't solve very much at all. We simplify. I'm gonna start giving you really complex problems and we will simplify. You have one job to do. Just pay attention to your job. Don't worry about the complexity. Just worry about your job. That's why I threw this picture up there. Or this one. You have one job to do. Do it well. School. Can you imagine walking to school? Man, person needs to go back to school. Or this one. You have one job here. Just make a straight line of red in between the blue. You run out of tiles. I wonder why. Goodness gracious. How about this one?
We still see school.
Well, I guess it's because it's so school. I don't know. Maybe your computer will catch up in a second. This one, make sure you stay in the bike lane. How about right turn only? And the road goes left. Made in China. With an American flag. How about that one? Or this one. Now this one, the person followed their directions. They had one job to do, and they did it great. So I just throw this in there kind of to be funny, spring break type deal, leading into it. But you have one job to do on chapter 5, and truthfully, what it's going to be is to simplify. Our end goal on chapter 5 is to simplify complex trigonometric functions. This word should have a complex there. Not like as in the textbook had it, but this I did not copy it. I'm just saying in general, if I were to write this, I would throw in the word complex trigonometric functions. That's the whole point of what we're doing in chapter 5. We will use identities to simplify. The identities are reciprocal, quotient, Pythagorean, cofunctions, even, odd, sum and difference. There's also multiple angle. There's a few more, but we will simplify trigonometric expressions, complex trigonometric functions. So I'm going to start easy. These first few problems are going to start basic, but I'm going to get into stuff like this. This is what you're going to look at chapter 4. Chapter 4, excuse me, we're on chapter 5. Chapter 5 are all problems like this. Notice all of them, none of them say solve. They just say simplify. You're going to learn how to simplify these type of expressions. So with that, let's go back to the start. We have a couple of vocabulary terms. The first is just identity. Identity is a way to represent something else. So for example, a driver's license is my identity. It's not me itself. It's like an identity. If you ever heard of identity theft, it's when someone steals maybe your social security and their credit card number, and they're not actually stealing you. We would have a different name for that. We would call that kidnapping. What they are stealing is something that represents you, the identity. So specifically, we're working with trigonometric identities. So here's a basic one you already know. Here's an identity of sine. Sine is y over h. That's an identity. If you have an angle in standard form, that's an identity. Cosine is x over h. That's an identity. We are going to be dealing with trigonometric identities, all brand new ones. Cofunction is one of those identities. Okay? So when math gets tough, I try to come up with an acronym to help you out. Spot oil doesn't mean anything other than it's a plan of attack for you when you're trying your homework on your own. Wait, what should I try next? Because When I get to example 4 and the rest of the way today, you're going to be asking yourself, what is going on? And what I would recommend you do is try to follow this pattern. It'll help you understand, or at least be able to complete the process before you totally understand even what you're doing. So I do understand we are dealing with, what was that word I added? Complex. We're going to be dealing with complex stuff here. And that's why I said you have one job to do, and it's to simplify. I don't want you, but it's going to be complex along the way. Just follow your one step. All right, with that, let's take a look at the first few identities they give us. So all year I've said that sine and cosecant are reciprocals. And we talk about reciprocal mean flip the fraction. Well, we always dealt with that identity. What this is also saying is you could just rewrite it as sine is equal to 1 over cosecant. That would be the same identity. Since sine is y over h, if you took the reciprocal and said you had h over y, well, that would be the same thing as cosecant. Whoops, CSC. Now, how do these two match up? Well, to get from here to there, you would have to actually say you're dividing it by 1, which means you're dividing that by 1. So sine is 1 over cosecant. Then that's what they have there. Notice this is more complex. So we started basic, we're getting more complex. Okay, so the reciprocal identities to show you that sine and cosecant are reciprocals, back and forth. Cosine and secant are reciprocals, tangent, cotangent are reciprocals. That's the reciprocal identities. There are 6 of them. Quotient identities, there are only 2. So that tangent is sine over cosine and cotangent is cosine over sine. Now, why is this? Well, we've learned that tangent is y over x. And if you remember my song at the very start in lesson 4.1, I said that sine is y and cosine's x. Well, why did I say sine was y? When technically it was y over h, and this was x over h. Well, the truth is when you set them up as a fraction, the h's cancel each other. They reduce. So that is sine divided by cosine. It's just the h's got reduced. And so all we're left with is y over x. So those are the quotient identities because it turns a tangent into a quotient. I know these are quotients, but they're also reciprocals because it's 1 over. So that's why they're different names. But they kind of go hand in hand. So let's start. And I'm going to start with just the basic. I'm not going to try to go complex yet. So how do we use reciprocal and quotient identities? Well, here's how we start. If cosine is 3/4, well, what's an identity of cosine? Cosine's identity is x divided by h. Is 3/4. Then find secant. Well, what is secant's identity? Secant's identity is h over x, which means secant would be 4 divided by 3. Okay, so I just started basic here. So you can just kind of see what we're doing. We're just using identities to substitute out and solve for what we need. Now, I wish it just stayed this simple, but you won't see another one ever that simple again. So let's try this part B here. If secant is negative 145 over 17 and cosecant x is less than 0, find sine and tangent. Okay, let's do identities here. Secant is h over x. So h over x equals negative 145 divided by 17. And I want to remind you of a rule we learned. H is always
Positive.
positive. That means h is positive 145 and x is negative 17. Now this is telling us something else that's important. It's telling us, cosecant, that h over y is less than 0. If I were to divide, we know h is 145. Let me put that in there. Okay, if I were to divide both sides by 145, easier way of writing this is multiply by 1 over 145. I could discover that 1 divided by y is still less than 0. Now, the only way 1 divided by any number could be less than 0 is if y itself were negative. If y is any positive number, then a positive divided by a positive is going to be positive. So this means that y has to be less than 0. It's the only way mathematically this can be possible. So y is less than 0. So what does that mean? If I want to do a little drawing here of a triangle, what we know is that x is negative 17. X goes left and y goes down. I know x goes left to negative 17 here. Let's do x, y. So x is negative 17. And we know our hypotenuse is 145. We could do the Pythagorean Theorem to come up with our y value. All we know is it's going to be the negative y value. So let's plug in our numbers here. We're going to use Pythagorean Theorem, x squared plus y squared equals h squared. I'm just going to type them in kind of as we go here. What do we know? X is negative 17, so negative 17 squared. I don't know the numbers off the top of my head, so there we go. What did I just do? There we go. I get 289. Actually, let me write this down. Why am I just doing it all here? So we're doing Pythagorean Theorem. X squared plus y squared equals h squared. So the x, negative 17 squared. We don't know y. We do know h. We just got 289 here. 145 squared, let's see what that is. 21,025, wow, what a large number.
If I have 1 fork, can they come here?
Yeah.
Okay.
Actually take that back. I'm leaving for a doctor's appointment. I don't know why.
I'll leave them a note. It's no problem.
Okay, I'm sorry.
It's not a problem. I
Yeah.
understand.
Sorry.
You mean your wife matters more than me? Oh my God. I mean, come on, dude. Yeah, good luck with that.
Yeah. All right, 21,025. And so to solve this, we'll subtract the 289. Why does it keep doing this? Sorry about this. Let's take off these arrows. And try this again. We'll subtract 289. And then we'll take the square root. Let's see here. So I'm going to subtract the 289. I get 20,736. And we take the square root of that. I get 144. We should say plus or minus, and we know that the answer is going to be the negative. We know that from right here. So it's negative 144. Negative 144. There we go. Just rewrite that. Negative 144. So it says find sine and tangent. And so now we can go and say, okay, what is sine's identity? Sine is y over h should be negative 144 divided by 145. And then tangent's identity. Tangent is y divided by x, which is negative 144 divided by negative 17. Question, 2 negatives. What happens with 2 negatives?
They become a positive.
They become a positive. All right. So there would be our solutions to this one. So I told you I was going to start basic. Well, I didn't stay basic very long. I know that one kind of took up the whole page there. But I have a DOL for you to try. It's a whole lot more basic than the one I just worked. So now let's see you try Dual number 1. Example 2. So let's start with the Pythagorean identity. So let's, before I actually start with the Pythagorean identity, let's start with the Pythagorean formula. Not formula, I'm sorry, theorem. I'll get there sooner or later. We have x squared plus y squared equals our hypotenuse squared. So what happens here? If you just think about this in terms of doing algebra in a different way. So I'm going to select this and clone it. I have the Pythagorean theorem written out here 3 times, 4 if you count that one. What I'm going to do is show you just common algebra. Let's say you took this and you want to divide everything by h squared. Remember, division is kind of like multiplication in that it distributes. So if I were going to divide over here by h squared, you'd have to divide everything on the left by h squared as well. Now, in this hypothetical example, if I did this, what would I be left with? Well, h squared divided by h squared is obviously 1. So anything divided by itself is 1. Well, x divided by h by itself would be cosine. So x squared divided by h squared is cosine squared. Just the same, y divided by h would be sine. So therefore, y squared divided by h squared would be sine squared. And so we get this identity. So it's not the same thing as the theorem, but it solves the same way. That's why we call it an identity, not the Pythagorean theorem any longer. We're now going to call this an identity. It's just another form of it. So how would I get this identity? Well, instead of dividing everything by h squared, I would divide everything by x squared. If I divided everything by x squared divided by x squared is 1. Y over x is tangent. So y squared over x squared is tangent squared. And then h squared divided by x squared is cosecant squared. I'm sorry, h squared divided by x squared is secant squared. Secant squared, there we go. And finally, over here, we've divided by h squared, we've divided by x squared. Now let's divide by y squared. If I divide everything by y squared, I come up with our last Pythagorean identity. That's cotangent squared. That's 1. And this would be cosecant squared. So that's where these come from. Again, we take simple math and we're making it complex. So I'm going to give you actually a basic problem where we just do the Pythagorean theorem, and we'll apply the identity here in a moment. So cotangent equals 2. Well, cotangent's identity is x over y, I'm sorry. X over y is equal to 2. So I'll make this a denominator of 1. This is a little tricky because it says cosine is negative, which cosine's identity is x divided by h. So if that's negative, we have a problem because when I multiply by h here, and h, since h is always positive, the inequality does not switch directions. I have that x is supposed to be negative, but I have over here x equals 2, which seems a little tricky at first until we consider this. This said cotangent was 2. It didn't say x was 2. It said cotangent equals 2. And we made that 2 over 1. But it actually can be negative 2 divided by negative 1. That's another way of getting positive 2. So this little problem here is a little tricky in the setup. After that, I think it's kind of basic. It just has those opening tricks. So if I wanted to solve this, my x should go left 2 units, my y should go down 1 unit. And our hypotenuse, we don't yet know. Let's make that y equals negative 1. This is x equals negative 2. And our h we could solve using the Pythagorean theorem. So I say theorem this time because that's what I'm using, just the theorem. We have negative 2 squared and negative 1 squared to be combined. So -2 times -2 is -2 times -2 is
4.
4. -1 times -1 is 1. And so h squared is 5, or h is the square root of 5. I would say plus or minus, but there's a rule with hypotenuse. Hypotenuse are always positive. So this is just going to be square root 5. So to find sine and cosine, I just use those identities right there. Sine is y over h, so it'd be -1 over square root 5. And cosine is x over h, so it'd be -2 over square root 5. Because we don't leave a radical in the denominator, I'm going to shoot it up. Basically what I'm doing is I'm multiplying top and bottom by a square root of 5. And so I get -1 square root of 5 over 5. I intentionally left off the 1. You could put the -1 there, but it just looks better that way. And here, when I shoot up the square root of 5, I'd have -2 square roots of 5 over 5. And that's my answer with a rationalized denominator. So now I'll give you one to try here, for example, 2. Here's yours to try. Let's take a look at cofunction identities and even and odd identities. So we briefly talked about this when we were dealing with chapter 4. Cofunction identities is telling you that basically sine and cosine will produce the same angle or the same solution if their angles are complementary to one another. Remember, complementary means adds up to 90 degrees. These are using radians. Pi is equivalent to 180 degrees, which 180 divided by 2 would be 90. If the two angles are complementary, you'll always get the same solution. So let me show you what I mean. What mode am I in here? I'm in degrees. Okay, sine of 60 degrees is not equal to cosine of 60 degrees. They are different answers. However, if you think about them being complementary angles, 60 plus 30 are complementary. These two answers would be the same solution. So the way they're writing this is it's saying like sine of, let's just say that's 60 will equal cosine of 90 minus that angle of 60. That's basically what they're writing out. And they're showing you that you will always get the same solution. Again, I could switch over now and show you in radians. Radians, you just have to change this to a pi over 2. Pi divided by 2. And notice these are the same answer now. So no matter what this value is, as long as they're complementary, you'll get the same solution. So sine of 20 and cosine of 20 are never equal. The only ones that would be equal would be 45 and 45 because those are complementary. But those are not the same answer. However, sine of 20 and cosine of the complementary, pi over 2 minus 20, would be equal. Let me switch back to degrees so this looks right. 90 minus 20, see how the solutions are the same. So as long as they're complementary, you'll get the same solution. Sine of an angle and cosine of its complementary angle. So sine of 1, cosine of 89, they would give you the same solution. That's what that would be there. If you reduced it, it'd be 89. Those two are complementary, so it's the same solution. Even if you go bigger than 90, 90 minus 100, it still works. Okay, so that's what cofunction is. It's just saying the relationships between complementary angles. Sine and cosine, tangent, cotangent, secant, cosecant. Now, even and odd. I'll do a quick little drawing here. Even and odd confuse a lot of students until they just understand, they really just lock on to sine being y, cosine being x. If you think in that terms, this even and odd isn't too bad. What a negative angle is, let me write this on there. A negative angle just means your angle goes downward. So if I compared a negative angle, so this is an angle that's going this way, that's a negative theta. with a positive angle going the other direction. Sine itself is the y portion. So what does that mean? If you have a positive angle, you would have a positive y. A negative angle would generate a negative y. So what does that mean? If you have sine of a negative angle, it's the same exact solution as if you took the sine of the positive angle, but then made it negative, because you'll still get the same y. All you have to do is make it negative and you get the same value. So let me show it to you. Sine of 100, let's make it a negative 100. Sine of negative 100 is exactly the same thing as not sine of positive 100, but a negative in the front. So this is saying a sine of a negative angle will give you the same values if you took the positive angle, but then made the answer negative. That's what's happening here. Sine of a negative angle is exactly the same as the sine of the angle being positive, but with the negative out front. Notice those match. Now, that works for sine. It does not work for cosine. Then let me show you why. So again, I'm going to do the same little setup. I'm going to take that portion if I can. Let's see if this works. Okay. But when you deal with cosine, you're now dealing with the x-axis. So notice, no matter if the angle is positive or negative, you're getting the same value of x regardless. A positive x. So the negative is irrelevant with cosine. It's even, so it doesn't matter if your angle is odd or negative or positive, you'll still get the same solution either way, because no matter if the angle is positive or negative, it'll produce the same x value. Tangent is like sine. It's odd. So let's see if I can copy it one more time. And move this over here. Okay. Tangent is y's divided by x's. So the x's stay the same, but your y's switch signs just like sine. So for that reason, tangent is just like sine. So let me show you the relationship all the way across. Cosine of negative 100, whoops. Notice that is not equal to negative cosine of 100. Those are not the same. However, cosine of negative 100 is the same thing as cosine of 100. Okay, so see the difference of those two. This is odd, this is even. Tangent's also odd. You'll see how those match up. So tangent's also odd. So that's the math there. So let me walk you through a problem or two using these two. It says if cosine x equals negative 0.75, find sine x minus pi over 2. So I'm about to show you a shortcut way of how to do this in the calculator moving forward. But to introduce you, this is kind of a, I told you on the example 4, we start getting real chapter 5 problems. This is kind of like an intro to chapter 5. So basically, here's what we have. We want to know what sine of x minus 2 will equal if cosine of x, whatever x is, produces negative 0.75. So here's how we would do this. We would try to use those identities. And so for you right now, you don't have them memorized, but I'm just going to show you as I go. What I notice about this is that pi over 2 is in the back, but on the cofunctions, we write them out front. So the first thing I'm going to do is I'm just going to reorder this and say sine of x minus pi over 2 is the same thing as sine of negative pi over 2 plus x. When you're doing your homework, Alex is going to ask you to name the step. That would just be called algebra. So I'll name it over here. So I really haven't done any math whatsoever. Now, again, you don't have these steps memorized. That's why I came up with that spot oil It's going to be a pattern for you to follow, but I'll start working through that in the next problem. So I'm just going to talk you through here. But the other thing I noticed is that these angles are all positive, or the pi over 2 is all positive. So here's what I'm going to do. This is a tricky step for a lot of students, is I'm going to do a GCF here. And I'm going to take out the negative. Now, what I want you to do is to envision this parenthesis as the theta. So I've made it be pi over 2 plus x, which matches the top, other than it's not a theta, it's an x. Whoops, I made a mistake. When I factor out a negative, I take a negative from both. So 2 negatives makes a positive, but I'm taking one of them away. I'm left with 1 negative. So that should look like that. This right there is also called algebra. Specifically what it is it's a GCF step. This was just reorganized. Alex will just ask you, and you'll just click algebra. There's a drop-down option, and you click algebra here. Okay, so I want you to envision this as sine negative, and the parenthesis is just being theta. So we have sine negative theta. So if I go to the even odd chart, even odd here, I have sine negative theta is equal to negative sine positive theta. So positive sine negative theta is equal to negative sine positive theta. So what does that mean for here? That means I have sine negative, and again, envision this as theta. That's equal to negative sine positive theta. What I do, I took the negative out and I moved it out front. That's because sine is odd, but what it'll say on the drop down is odd even identity. Sine is odd. So I'll underline it just so you know, it's odd. Okay, now from here, I can say, all right, now I have this as a cofunction. So sine, and this is saying of a complementary angle. So what is sine of a complementary angle equal to? Sine of a complementary angle is equal to cosine. So this is going to become cosine right there. And I'm just going to drop down the rest. It's going to equal negative, so you can see that negative drops, negative, and this became cosine. And that right there is from the cofunction identities. It's a cofunction identity. And now, last little substitution. We know cosine is negative 0.75. Again, I'm going to drop this negative down. So I have 2 negatives. All that would equal the sine of, actually, I'll write one more time. 2 negatives make a positive, so it'd be positive 0.75. That's sine x minus pi over 2. All right. So, as you just saw there, that was some complex math. Well, what in the world just happened? You might be thinking. And you will be thinking that probably for the next 2 class periods, is my guess. That is just applying a lot of identities. Oh, by the way, this last step would just be called algebra because we substituted. So I'll write in here, algebra, specifically we substituted. Not that you'll have to put that part in Alex, but I'm just writing it out. Okay, so how could you use a calculator? I told you you could use a calculator. How could we? Well, if you use the calculator, you would just think through, how would I solve for x here? Answer is, I would do an inverse. If I need to get the x, I need to isolate it. And so the way you deal with functions is you do the inverse function to swap those two. So what I'll type in the calculator is cosine inverse, and I'm going to put it in parentheses here, negative 0.75 is going to equal my x value. Now, for the sake of solving in the calculator, I'm going to need to make this like an x1. because it won't solve it if I just put an x. So I'm going to come over here, and I'm going to show you one thing I wish Desmos would solve, but I want to show you this problem. If you type it out like I wrote it, Desmos, for whatever reason, does not solve it. However, if you put x1 in the front, it will solve it. You might be thinking, why on earth are you putting the 1? Well, because if I don't, it won't actually store the answer. It'll show me a vertical line where the answer is, but it won't store it. And so when I now want to find the answer, I could type this in, but it won't do anything with it. Watch. I'm going to put an x1 there. Pi over 2. When I type this in the calculator, if I don't put the x1 here, if I just leave it as x, nothing will happen here when I type that in. X minus pi divided by 2. It just gives me a flat line, and there's no solution. Notice that does not match. So what do we do wrong? We need to put the x1 there and put an x1 here. If you use x1s, all of a sudden we get our answer. It's because I'm in the wrong mode. 0.75. Okay, interesting. I'm wondering if I don't. Could it work this way? Wow, it does. How about that? I didn't know it'd work that way. So that time I just typed it in as equals x, and it worked. But it's probably easier just to do x1 and x1, and you get the solution. They match. All right, let me try another one for you, so you can see it one more time. So here's the algebra again. So I'm starting with that cosine x minus pi over 2. And the first thing that I would realize is, now knowing I know the spot oil stuff, the problem solving technique, the first thing I realized is this is an other identity listed. This is an oil one, where pi over 2 is supposed to be in the front. So I would reorder first off. So I'm going to have a negative pi over 2 plus an x. And you'll get this down. It just takes a little practice, more than one day worth of practice. That is algebra. I just reordered. That's all I did. Okay, next, I need to get that pi over 2 to be positive, because this is going to be used for that complementary angle. But we don't talk about being negative 90 degrees or negative pi over 2. We need it to be positive. So what I need to do is factor out that negative. Oops, let me do a bracket like I did last time. Bracket, negative pi over 2. And since I'm taking a negative from both, this becomes a negative x. That is algebra. Specifically, it was GCF. GCF. Okay, so now I want you to envision this as being negative theta. So it's cosine negative theta. Well, cosine is even, which means it doesn't matter if it's a negative angle or a positive angle. It's still going to produce the same answer. So honestly, I don't even need this negative there. I can remove it. I don't need that there. So I can say this is equal to cosine of pi over 2 minus x. That's using the even odd identity. Specifically, this one's even. Okay, now I have this in normal cofunction form. This is saying cosine of a complementary angle. Well, cosine of a complementary angle is equal to sine of its complementary, which is just x. That right there is called cofunction identity. And we know sine x is equal to, that right there is equal to negative 0.75. So our cosine of x minus pi over 2 is equal to negative 0.75. So I want you to see the difference in these two. This one, we started negative 0.75 and we worked through the problem. It became positive 0.75. This one started negative and it ended negative. Why did it not switch signs like the previous problem? The reason has to do with cosine being even. When I factored out the negative had zero impact on the problem. So it didn't change any value. Sines and tangents, the negative matters. If you have a negative that you factor out, it's going to make your answer negative. And so this negative became negative again, and two negatives means it became positive. Okay, so you can just think through when you do this problem. If I factor out this negative, what effect will that have on sine? Will it turn my answer to the negative, or will it not have an impact at all? Or you can just use calculator mode as well. DOL number 3. Example 4. Now this is where we truly get into example or chapter 5. The rest of the way, we are for the most part going to just be simplifying. Not solving, but simplifying the rest of the way. So how do we simplify? Well, the first thing I would recommend you do is follow the acronym SPOT OIL. You're going to hear me say this a lot. This is just you don't have to follow this order. It's just a way for you to methodically work through how to try to simplify a problem like this, because a lot of students, simplifying this becomes very tricky. So the S actually stands for simplify. So I'll just write that in, simplify. And specifically, the two ways to simplify are using algebra to cancel, simplify being cancel, or to use factoring to simplify or factor. I just call it S for simplify. P stands for Pythagorean. So remember there's those different Pythagorean identities. That's the second thing to try. O stands for opposite denominator. Opposite denominator. And this is at the front of the lesson. If you download a complete set, you'll have this. Okay, denominator. There we go. I knew I was missing something. Trying to figure out what am I missing. T is transformed to sines and cosines. And the oil is other identities listed. Specifically, we've had cofunction and even odd. And on day 4, we will have another one given. Okay, sum and difference identities are going to come later. So let's work through this. The first thing you need to check is, can I simplify or factor anything? So you look at it and say, okay, can I cancel anything? Can I cancel these ones? Can I do anything like that? Or is there something shared that I can factor? And the answer is no. So you go on to step 2. Can I do Pythagorean? With Pythagorean, what you're looking for are ones and squares. So I'm going to just do ones and I'm going to draw a little box here for squares. And the answer is yes. I have a 1 and a square right there. So I'm going to use that Pythagorean identity. Let me go to my notes. And I'm going to open up the formula chart. It's listed right under digital resources, right under the YouTube link. If you click that. This is hard to see. Let me zoom in. Here are my Pythagorean identities. There's 3 of them. You remember earlier when I was dividing by the x squared, h squared, and y squared. So this one has a sine. So I'm looking at the one with the sine. Whoa, what happened there? I'm looking at this identity with the sine. I need it to be 1 minus sine squared. Well, this formula right now is set up as sine squared plus cosine squared equals 1. So if you just think through some basic algebra, if sine squared plus cosine squared equals 1, then basic algebra would tell me if I subtracted sine squared, I would have cosine squared equals 1 minus sine squared. I just subtract the sine squared across. And so that's what I'm substituting right here, is I'm going to substitute this and say we have 1 over cosine times, and here we write sine squared. That is the Pythagorean identity. Okay, so what I did is I saw that we had a 1 and a squared, and so I substituted it using Pythagorean identity. That 1 minus sine squared. Oh my goodness, that's not equal to sine squared. Check me. What should I have written right there? What is 1 minus sine squared equal to? 1 minus sine squared. What's that equal to?
Cos squared x.
Cosine squared. That's right. This should have been a cosine squared. So that's a Pythagorean identity. 1 minus sine squared is equal to cosine squared. So now how do I solve? Well, I look at it and I start back on spot oil. Ask, can I simplify or factor anything? Answer is yes. I'm dividing by a cosine and I'm multiplying a cosine. So this one can be simplified. Let me switch to orange. I could say that dividing cosine and this multiplying cosine, one of those two that are multiplying, can be canceled out. And I'm left with 1 times cosine, which is simply cosine. And I got that by doing algebra. Specifically, we simplify. And so all of this right there, let me actually write this out more. This would become 1 over 1 times cosine. And so if I wrote it all the way out, you could see that 1 over cosine x times 1 minus sine squared x equals cosine. So there's the start, there's the finish. Let me prove it to you. The nice thing about chapter 5 is that although the problems start very complex like this, weird stuff, and you do a lot of weird math, we do spot oil, the math itself is the easiest to confirm whether or not you got it right or wrong. It's the easiest to decide, did I do this right? Did I do it wrong? Why is it so easy? Well, all you have to do is graph. These are supposed to be congruent to one another, which means the graphs should match. If I did y equals the left side of the equation, 1 divided by cosine x times 1 minus sine, 1 minus sine squared x, that graph better equal 1 or y equals cosine x. Do the graphs match each other? Yes, they do. So we did it correctly. They match. Okay. So here's one for you. You go ahead and try to match graphs to come up with your answer. That's what I would recommend here. And I'll try to come back maybe next lesson and work through this algebraically. But for right now, try to work, just use a graphing technique to see which one's equal. All right, let's take a look at example 5. So this is more spot oil. And truthfully, you're going to see me write spot oil on almost every problem the rest of chapter 5. We just have to add in another formula into oil. So it says solve by factoring. So here's the problem solving steps. Remember, first we look to see, can I simplify or factor? So you're looking across and seeing, is there anything I can cross out? Or is there anything shared that I can factor out? And the answer is no. So then I go on to Pythagorean. I look for ones and squares. Do I have any ones in squares? Well, I do have a square, but it's not by itself. So I can't do Pythagorean when it's attached to something. So I can't do it yet. O stands for opposite denominator. You haven't seen that yet. We'll see that in the next example. So I skip that. T, transform. That's where I'm at now, and that's what I'm actually going to do. Transform is where you take this and say, okay, I'm going to transform anything that's not a sine or cosine, and I'm going to make it a sine and cosine. So let me put dots there so you can see what I'm doing. I'm going to take tangent and say, okay, sine's y, cosine's x. Tangent is y over x. tangent is sine over cosine, which that right there is called the reciprocal identity. I'm just going to write it up above because I'm going to do 2 steps in 1 here. Now I have minus sine x cosine squared x. What am I talking about? I thought I was going to do 2 steps in 1. I'm only doing 1 step. So I'll write it there. That's a reciprocal identity I just did. Okay, and so now I start over spot oil. I go back and say, can I simplify or factor anything? Answer is yes. Now I can simplify. I have cosine divided by cosine. So now I have sine x minus sine x times cosine squared x. On Alex, they call that algebra anytime you simplify like that. I cancel. So now I start over again. Can I simplify or factor? S stands for simplify or factor. Is there any GCF or anything that cancels here? I can't subtract because sine minus, this is sine cosine squared. It's not the same. So they're not common terms. So I can't subtract, but I can do a GCF. What do these both share? Yes, x, but trig function. What do both terms here have? They both have sine. So if we factor out the sine, sine divided by sine is 1. It's like the opposite distribution, pulling out the sine. And over here, I'm left with cosine squared. This is also called algebra. Specifically, that's a GCF. And so now I'm here. I start spot oil again. Can I cancel? No. Can I GCF? No, we just did that. Pythagorean, P. Do we have a Pythagorean? Yes, I have a 1 in the square. So I'm going to go to my chart. It's 1 minus cosine squared, which to get that would be as if I subtracted the cosine squared over here. So that means the only thing that would be left over would be sine squared. So sine squared is going to equal 1 minus cosine squared. So that's what I have here. Is we're going to say that right there is equal to sine squared. And that was doing Pythagorean identity. And so now, final step, I can simplify. Sine times sine squared is sine cubed. And that step would be called simplify. Oops, no, on Alex, they'd call it algebra. So all of that equaled sine cubed. You could check your answer by graphing these. What's tricky on Desmos, if you have more than one trig function as a term, you need to put the parentheses around the x. So if you're going to check this by graphing, you would have to say it's cosine, and you'd have to put the parentheses around the x, times tangent x minus sine of x cosine squared of x. If you do it like that, you should get a graph. And then over here, we said the answer is sine cubed of x. Why is it not graphing? Okay, you put the cube there. Will it work? Yeah, there you go. I don't know. That's weird. It doesn't take sine cubed in the normal spot. You notice those graphs are the same. And here would be a problem for you to try. I would recommend graphing this. Just make sure you use degrees because that's in degree mode there to get your correct solution. All right, example 6. Let's see opposite denominators. So I'm right up here, spot oil. So what is opposite denominators? Opposite denominators is when you look at and you have two fractions like I do here, or at least two, and the denominators themselves look like they're just opposite of one another. This is what we actually call a conjugate. So that's what I'm doing this step here. It's technically called a conjugate. And the way you solve is by getting a common denominator. So I start with what I have right now in each fraction. So I have secant x over 1 minus secant x. And if you remember your old fraction rules, if you want to combine two fractions, you get a common denominator. So the left has 1 minus secant. It needs to be multiplied by 1 plus secant. Whoops. Kind of combine the c and the x there. There we go. And if you do something on the bottom, you also have to do it on the top. It's kind of like multiplying by 1 here. So mathematically, that stays the same. Now I'm going to have on the second fraction, I start with secant over 1 plus secant x. Now again, if I'm going to combine these, I have to have a common denominator, which means I need to multiply this second fraction by 1 minus secant x. Okay, so let's multiply these out. On the denominator, I'm going to need a FOIL. By the way, that step right there is called conjugate. I'm going to FOIL, and the top, I'm going to distribute that. Okay, so what will I be? And I know I'm going to have a common denominator. I can see that. The denominator is the same. So when I FOIL here, I have 1 times 1. And then 1 times secant. Negative secant times 1. And a negative secant times a negative secant, or a positive secant. So negative secant squared. Up in the numerator, when I distribute, that's all I'm doing here, distribute. I'll have secant times 1, so secant. Secant times secant is secant squared. I'll have minus, and I'm going to distribute the negative secant through here. Negative secant times 1 is negative secant. And negative secant times another negative secant is a positive secant squared x. All of that was the conjugate. Which I can't remember if Alex calls that a conjugate or if it calls it algebra. That's what I did there. Now, what I do know is I'm going to simplify this, and that is called algebra. So I have a positive secant and a negative secant in the denominator. Those cancel out. Up top, I have a positive secant minus a secant. Those cancel out. So it looks like I have 2 secant squareds. I have a secant squared and another secant squared, so I have 2 secant squareds over 1 minus secant squared. And that right there is called algebra. Now, the point in doing a conjugate like this is anytime you apply a conjugate, you'll always end up with a Pythagorean identity. So I'm looking for 1 minus secant squared. Now, this one's a little bit trickier. So here's my secant squared. There's my 1. I would have to make it 1 minus secant squared, which means the secant squared would have to move to the left. But I have a tangent over here that needs to move to the right. So for secant, when it moves, it becomes negative. Same thing with tangent squared. When it moves, it becomes negative. So this little Pythagorean identity, let me just show you this way. 1 plus tan, if I'm going to do this right, I need to change colors. Tangent squared theta equals secant squared theta. Here's what I was saying for the formula chart. If I want to move the secant over here, I got to subtract it. And so it becomes a negative. But I want the tangent gone. So the way it moves, it also becomes negative. And so now I can see that I have 1 minus secant squared is equal to negative tangent squared. So that's the little algebra I did from this formula right there. And so let's write that out. We have 2 secant squared x over a negative tangent squared x. That right there was the Pythagorean. So we did conjugate first, and then I did a little simplifying algebra, and then I did Pythagorean. And so now I go back and say, can I do any simplifying? Well, nothing cancels. I just did Pythagorean. I taking care of the opposite denominator, that's gone. Now I can transform. Okay, I'm going to change things to sines and cosines. So secant squared in the numerator, secant is the same thing as cosine in the denominator. That's a reciprocal right there. So what I'm going to do is this secant is going to move down as a cosine. So I'll have 2 over cosine, and I'm going to actually move it right in front of that negative. It'll be easier. Actually, I'll just put the negative right there. I'm going to take this negative, and on a fraction, it doesn't matter where you put it. I'm going to move the fraction up just to make it easier. And so I now have the cosine squared x there. So that secant will move down. Secant moves down, becomes a cosine. And now I have tangent. Tangent, you can do one of two ways. You can either take tangent from the bottom and make it cotangent up top, or you can just think about it's sine divided by cosine, which means sine, since it's down, the denominator is backwards. It's kind of like sine down here. This is going to break, and so this is going to become sine. It's usually sine over cosine, but since it's the denominator, it's going to be sine under cosine. And so I did two things there. I did a reciprocal identity. That's the blue, the reciprocal, and the red is called the quotient. And then finally here, I could simplify. Cosines cancel each other out. -2 over sine squared. That right there is algebra. And I said finally, but I realized I got one more step now. And the last one here, let me just put this. Okay, and finally, last step. I can now shoot my sine squared up. So sine in the denominator, same thing as cosecant in the numerator. So I can shoot that up, doing a reciprocal identity, and I get -2 CSC squared x. That's using reciprocal identity. All that would be equal to where we started off, this portion right there. Now, I'm not going to rewrite that just because I've gone long enough on that problem, but all of this should match the graph of -2 cosecant squared. So now I have one for you to try. Again, you can use graphing technique to try to come up with your solutions. This one's a little trickier, but I would still do an opposite denominator on this portion here. I would multiply this by 1 minus cosine, that fraction. All right, example 7 says rewrite 1 plus tangent squared x over cosecant squared as an expression that does not involve the fraction. All right, so let's do this. So we have 1 plus tangent squared x over cosecant squared x, and I want to follow spot OIL. So the first thing I'm going to check for is, it looks like I have a 1 squared. I would say simplify, but nothing simplifies. I have 1 plus tangent squared. I check my formula chart, and I notice right here, we have 1 plus tangent squared. That's equal to secant squared. So that right there was the Pythagorean identity. And now from here, let's see. I can't cancel anything. I can't do Pythagorean. I don't have ones there. I don't have opposite denominator. I could transform sines and cosines. Okay, so secant and the top is like cosine the bottom. So that's going to shoot down because it comes to cosine squared. And then CSC in the denominator, CSC in the denominator is like sine in the numerator. That's its reciprocal. It's going to shoot up. So that one shoots up. Sine squared x. So what I did there is 2 reciprocal identities. So now I have sine squared over cosine squared. We don't want a fraction. So let's see, can I simplify anything? Nope. Can I do Pythagorean? No, I don't have ones and squares. Okay, I do have squares, but not ones. Opposite denominator? Nope. Transform, well, I'm kind of transformed. This is kind of like the opposite. I could simplify this saying, okay, I sine over cosine, or sine squared over cosine squared. That's like tangent. Sine's y, cosine's x, tangent is y over x. It's just going to be tangent squared. So this right here is tangent squared x. That right there is called a quotient identity. So all of this would be equal. And again, you could check by graphing y equals and graph this, y equals tangent squared, and check to see if the graphs match. Here's one for you to try. You can use whichever technique you prefer. All right, when we come to ACP time, we have these problems. These are review problems. You'll notice that usually on the ACP, it's not these type of problems, or you can just solve by graphing. So I don't like them being here. So I just want to review you. Secant, let me pull this up. Secant is h over x. So this is saying h over x is equal to negative 25 over 7. As by rule, the h is always positive. So I'm going to put the negative with the 7. And this says tangent is less than 0. By identity, tangent is y over x. X we know is negative 7. When I multiply by negative 7, anytime you multiply by a negative with the inequality, it changes direction. So this says y is greater than 0. Y is positive. We want to know what's the answer of CSC, which by definition is h over y. We know we have a positive 25 for h, and we know we have a positive y, some positive number. So these two are out because they have negatives, and it's got to be j. H has got to be bigger than the y, so it'd be 24. You could do Pythagorean theorem just to confirm. X squared plus y squared is going to equal h squared, where you know your x is negative 7, your h is 25, and you can confirm that y is going to be 24. Now, reference angle. A reference angle is the angle that connects to the nearest x-axis. So if you think graphically, 840, where would that be? So we're going to compare to the nearest x-axis. So remember how this is 0 degrees at the start, and this is 180. And then if you go all the way around, you find out the 0 is equivalent to 360. And if you went around again, you find out 180 is equal to, let's see, 360 plus 180. I'm getting 540. We're still not there. I keep going around. This is now equivalent to 720. So I'm getting closer. I only got 120 more left to go. There's 90 of them and a little bit past. They're right there. I'm going to say that is 840 degrees. And so a reference angle is the angle that connects it to the nearest x-axis. So the reference angle is going to be what is the angle that connects from here to there. That's the reference angle, which we show with a O theta. Okay, and so if that was, if you remember, I said 720, 840 minus 720 is 120 degrees. That means from here to here is 120. So how many degrees is it from 120 to 180? It would be 60. And that's my answer. You could check in the calculator for reference angles. You ignore the positives and negatives, but you can use any single trig function and you should always get the same answer, just minus the negatives and positives. Let me make sure I'm in degrees, not degrees. There we go. If you ignore the negatives and positives, meaning like you take the absolute value, the reference angle should always work out no matter which trig function you use. So you can see all these answers are working out. Just the numerical values are the same minus whether or not they're positive or negatives. Okay, so that's another way of doing reference angles.